also becoming a part of hiring and so on, right? So as machine learning models are increasingly being deployed, especially for assisting these kinds of critical decision making, interpretability becomes key. Okay, only if the decision makers who are actually working with the machine learning algorithm or the AI algorithm, if they understand what's going on or how the model is making predictions or what is its rationale behind the prediction, they'll be able to make an informed decision about whether they would like to agree with the model or disagree with the model and so on, right? Okay, so, given that interpretability is so key, especially in a lot of these kinds of settings where we envision humans and algorithms will be working together to hopefully make better decisions, what are our options, right? So, what are our options in the ML literature? I think roughly we can roughly agree that probably simpler classes of models are somewhat more easier to understand. Of course, I say that with a caveat in the sense that, if you give me a 100 level decision tree, maybe it's hard to understand, but assuming we are talking about shallow, sparse, simpler models, they are somewhat easier to understand relatively compared to something like a deep neural net or a huge deep neural net, right? Okay, so for example, linear models or decision trees, again, sparse decision trees or shallow decision trees, sparse linear models, simple rule-based models, these are somewhat easier to understand. However, there has been a lot of research in the past decade or so which has shown that complex models can achieve comparatively higher performance than simpler models. And when I say complex models, these could be large deep nets, random forests, gradient boosted trees, and other kinds of ensemble models, right? Especially when the data is high dimensional, like we have seen examples in the case of vision and NLP, and even, larger high dimensional tabular data sets, that complex models could perform better compared to simpler ones, right? So given this kind of a tension between accuracy or like superior performance and understanding the models or interpretability, the solution that the community has come up over the past few years, or at least which has become popular over the past few years, is that let's build complex models and let them be as complex as you can in order to achieve higher accuracies. So build such models, just go for accuracy. Once you have built such a model, then try to explain these models using other simpler models, right? So build as much as you want, as complex a model as you want, and then make it as accurate as possible, and then leave that model as it is. Then use some post hoc approaches to explain these models using simpler techniques, right? Like again, the simpler models or simpler techniques could themselves be again linear models or simple rule based models and so on. So, this broad solution or the class of approaches that fall under this broad category have been called as post hoc explanation techniques, right? So, that's roughly what I mean when I say post hoc explanation techniques. And most of this talk or all of this talk is about post hoc explanation techniques, right? So, the agenda for today is that we will give an overview of post hoc explanation technique. I'll talk a little bit about the challenges of post hoc explanation techniques, and then I'll talk a little bit about our first work, which is explanations with guarantees, how to mitigate some of the challenges that we are discussing in the first part and propose a solution to address some of them. So, that would be the second part of the talk. And then I'll be spending very little time and giving a quick overview of another approach, which is based on adversarial training that we proposed, where the goal is to make explanations or generate explanations that are robust to distribution shift. And lastly, we'll end with some conclusions. Okay, so in the first part of the talk, I'll mainly be focusing on a certain class of post hoc explanation techniques, and in the second part, we'll also look at few others. Okay, so let's start with this post hoc explanation techniques, right? So as I just described, the goal here is to basically explain a given complex model using simpler models in a post hoc fashion, right? So typically, a lot of these approaches consider the complex model as a black box. You need little to no internal details of the model. Most of them require like a query access. For example, we should be able to send in a point to this complex model and then get some output, right? That is query access. So several of the techniques that we'll be discussing today just require query access. But there are also a few other techniques which try to post hoc explain a given complex model, and they need a slightly higher degree of access, which means they require access to the gradients of the underlying model, right? So roughly, this is the level of information that post hoc explanation techniques actually need in order to explain a complex model. And there are several types of post hoc explanation techniques, local explanations versus global explanations, where local explanations means you're trying to explain the rationale behind individual predictions of a given model. Global explanations, as the name suggests, means that you're trying to explain the complete functionality of a given model, right? And that is, of course, the type of explanation. Then there is also this kind of a classification based on the approaches that are developed to explain these models. For example, some are based on gradients, some are based on what we call perturbations, and I'll explain in a second what I mean when I say perturbations, right? Okay, so just to kind of name drop a few things here, I'm sure several of you must have heard about methods like LIME, SHAP, Anchor, Muse, gradient-based approaches, integrated gradients, GradCam, smooth grad, and so on, right? So the first part of the talk, we'll focus on LIME and SHAP, and then in the second part, we'll go to some more general approaches and also put some focus on global explanation techniques. So I'll talk about that in a bit. Okay, so in this part of the talk, we'll mostly look at local explanations. What do I mean by local explanations? As I just mentioned, the goal here is to explain the rationale behind individual predictions of a given black box model, right? Why do we need this kind of a local explanation? It can help us vet if individual predictions are being made for the right reasons, and they're not being based on some spurious attributes, and it can also help us unearth biases in the local neighborhood that we are looking at, right? So which is around the instance that we are looking at. Okay, so two of the popular methods in this class of local post hoc explanation techniques are called LIME and SHAP. Let's look a little bit into what these methods are. So these methods are basically local explanation methods. So they're model agnostic in the sense that they do not need to know the internal functional details of the underlying model. They can function with any model, and all they require is query access, right? So we should be able to input a point to these methods, or we should be able to have a black box models into which we can input a point and get a prediction. So all we need is that level of access to the model, and using that level of access, these methods can generate explanations. Now, both these methods output feature attributions for individual instances, which means think of it as like the output feature importances, right? So the term feature attributions is being used, but like that's roughly the same as like feature importances, which capture the effect or contribution of each feature on the black box prediction. Okay, so these methods, they're model agnostic. They only require query access to the model, query the model, get the output, and they output a list of feature importances, right? So that's the summary. Okay, so let's talk a little bit more about these methods. How are they doing this? How are they functioning? So I'll be focusing this discussion a bit more on LIME from here on, just because it is kind of easier to understand and get an intuition for. But a lot of what I'll be saying also applies to another method called SHAP, which is pretty related to LIME and is basically like a game theoretic version of LIME. Okay. All right. So what are these approaches like LIME and SHAP doing, right? So the hypothesis or the intuition that these approaches are exploiting is that while complex models can have complex decision surfaces, and could be harder to explain globally. For example, if you look at this picture, you see two regions, the blue region and then the light pink region. Both of those are kind of separated by a highly nonlinear decision boundary. Right, so we can think of that decision boundary as a classifier decision boundary of a complex classifier. So while it is harder to explain this rather complex decision boundary, the intuition that these approaches put forth or like exploit is that if you zoom in enough and look into a small portion, for example, if we zoom in around this point, which is marked by this red plus mark, we see that the model is behaving like a linear model, right? So though globally it's a very complex decision surface, if we zoom in enough and look at the small pocket, this complex model is behaving like a linear model, right? So that's exactly the intuition that these approaches try to capture and generate explanations or post hoc explanations. And what do they exactly do? Here is what they exactly do. Again, we are talking about LIME. So the main idea or intuition behind LIME is that, let's take a data point and let's say we want to explain the rationale behind the prediction of this data point. Okay, so we take the data point, we perturb it slightly, and then generate a bunch of points around this data point, and then we fit like a linear model on these surrounding data points, and that linear model will basically explain the local behavior of the underlying complex model. Okay, so that is the intuition, right? So take a point, perturb it slightly, generate a bunch of points around it, you got some local neighborhood, now fit a linear model which predicts what the underlying black box is predicting, and you got yourself a local linear model which will give you a list of feature importances, and that will be your explanation, right? So how do you generate these perturbations? That is, I think, one of the key points, and there are a variety of ways to do it. For example, add some Gaussian noise if you're looking at continuous features. And one other way that is sort of suggested, at least in the LIME paper that was put out first, was that binarize all the features because they were trying to apply their method to a variety of data. So what they suggested is take all the features, binarize them, so every feature will have a value of 0 or 1, and for all those features that have a value of 1, sample a random subset of those features and change their labels to 0, right? And then we get a perturbation. Of course, there has been a lot of discussion on, is this really a valid perturbation, what kinds of points is it generating, are these out of sample, and so on. But I'm not going to go into all those details, and we'll focus on a few other aspects. Okay. So what do LIME explanations look like, right? I was talking about LIME outputting like a list of feature importances. Roughly, that is what is shown here. So if you look at this, here are LIME's feature importances for a particular point in the famous Compass data set. And if you see like the feature importance of this feature misdemeanor charge is somewhere close to 0.23, and the feature importance of this feature female is somewhere close to minus 0.125. So red is negative, green is positive contribution. Okay, so yeah, it's basically a bunch of feature importances, right? And if we look at like images, in this case I'm just showing you the top 3 superpixels or the features of the image that LIME thinks is most important for its prediction. As you can see, it is highlighting some pieces of the guitar string, the face of the dog here, some notion that it's an electric guitar, and so on. Okay, so roughly this is what LIME is producing as an output. All right. Okay, so let's take a look at the formulation of this a little bit more so we can use it later and try and improve it, right? So what LIME is doing, even in terms of formulation, is intuitive and simple and nice to understand. They're essentially minimizing this function, which is a sum of a loss function and a complexity function. So let me first touch upon this complexity function. This pretty much is, saying that the smaller the complexity of the model, the better it is, right? So for example, in case of linear models, we can think of it as number of non-zero weights in the linear model explanation. right? So the fewer the number of non-zero weights in the linear model's feature coefficient vector, the easier it is for us to understand, right? So fewer features with non-zero weights. So that's the goal. Okay, so we are trying to minimize this kind of a metric. And the loss function is actually very similar to like a standard supervised learning loss. But here, what we are trying to see is, if you look at this first term here, we are trying to minimize the gap between F is the model, the black box, the predictions of the black box, and the predictions of the explanation, which is the local linear model, right? So that is what we are trying to do. Okay, and Z is the local neighborhood that I was just talking about, that we are creating by generating perturbations. Okay, but one additional thing that's happening here is that there is like a distance function, which could be thought of as a cosine distance between a given perturbation Z and the original instance X. Okay, so the idea here is that perturbations that are farther off from the instance that we care about, those should be weighted less, right? Because they're probably not even in the local neighborhood, so we should not care too much about optimizing for them, right? Whereas perturbations that are closer to the instance that we are considering, those should be weighted highly, because those are important, those are in the very close proximity of the original instance, right? So that's the goal. So that's why there is almost like a weighted function here. Otherwise, it is pretty much about saying, let's match the predictions of for each of the perturbations. Let's match the predictions between the original black box model and the local linear model, which will be our explanation. Okay, so that's what LIME is doing. All right. Now let's talk about the challenges associated with LIME, right? So the first one being fidelity. And what do I mean by that? So a key question that comes up as soon as we generate anything like a model or an explanation is, how good is this, right? So in this case, we could ask, are LIME explanations faithfully capturing the behavior of the underlying models, right? Very good question should be asked. But the answer is not so simple, right? So there have been several efforts to kind of, try and understand how to articulate or like quantify this, how to capture the faithfulness or the fidelity. I'll just kind of touch upon one, and then, just to give you some idea about, there could be some problems with measures also, which are designed to evaluate the faithfulness or fidelity of explanations. So, for example, one approach that has been popularly used in actually a bunch of papers is compute weighted R square on the generated perturbations, right? So, we talked about in the approach line, you take a point and then you perturb it and generate a bunch of perturbations which form the local neighborhood, right? So, take those perturbations and then compute a weighted R square, or something like a weighted accuracy on those perturbations, with the ground truth labels as the labels of the original model, right? So while this approach might seem reasonable when you look at it at a first glance, the problem is this is making the evaluation dependent on the perturbations generated by LIME itself. What if those perturbations are not a good approximation of the local neighborhood? What if those perturbations are not reliable? So, which means our metric is entirely dependent on what the algorithm is doing, right? So, given that, this measure can be very iffy, and several works have also argued that this is not reliable. Okay, so while there have been other approaches, like let's use some synthetic data, synthetic models, they have their own limitations, and there is no like one standard agreed upon way of like, this is something that we can use to evaluate the goodness of any explanation. All right, so there is more. There is another challenge, which is stability. What do I mean by stability, or rather lack of stability? Small changes that you make to an input data point can cause drastic changes in explanation. right? So this is something that was defined in a paper where they propose this measure of local Lipschitz constant. And if you can see, this is nothing but the ratio. Here, f is actually the explanation function and not the model, unlike some of our previous slides. But basically, you are trying to compute the distance between the explanations as you vary the distance between the instance and its perturbation, right? So ideally, this distance should be smaller in order for the explanation to be stable, right? So intuitively, this is that if I take a point, add very little noise to it, the explanation should not just be drastically different, right? So it should still be pretty close, pretty consistent with what is the explanation with the neighboring point. Okay, so that's what this property is trying to enforce. And again, LIME and SHAP face problems here. So these approaches, if you look at this plot, they have plotted the local Lipschitz estimate. And what this plot shows you is that both these methods have like pretty high values of stability across multiple data sets. And, that's not really very desirable, right? Then we also found in one of our approaches that Lime is not just unstable, but it is also inconsistent, right? What do I mean by that? Oops. Sorry about that. I had a internet glitch and then I lost my connection, but we are back again. Let me just share my screen. Okay, all right. Okay, so just to continue the discussion, we were talking about line being unstable and also sharp explanations being unstable. But there is a bigger problem, which is that these explanations are not even consistent. What do I mean by that? So if I basically take a point and get its run line on it repeatedly, right? So I'm not changing any parameters, I'm not changing anything in the setting. I'm just taking a point, taking a model, repeatedly trying to run Lime on it. Even then, Lime can generate different explanations. For example, if you look at these last two plots here, so what you see in this blue region is basically the range of explanations that Lime is generating. Okay, so each explanation corresponds to one single blue line, but you can see that there is a whole area that it is tracing, right? So that is probably a even bigger problem than stability and some of these things, right? Okay, so the thing that you can also see is that if you have fewer number of perturbations, this band or this area is like much larger, whereas if you have many perturbations, this band is actually smaller, right? So it's tighter. So one could argue that maybe this problem will go away if you just have a very large number of perturbations, right? Well, that might be true, but nobody knows what is the optimal number of perturbations, right? And can we just use a very large number of perturbations? That has other issues, which is that of scalability. Okay, so querying complex models like InceptionNet, ResNet, AlexNet, and so on repeatedly for labels can be extremely computationally expensive, right? So the more we can limit this kind of querying, the more faster we can run these algorithms and generate explanations, right? But large number of perturbations actually implies that they will have large number of model queries, which is again going to be computationally expensive. Okay, so generating reliable explanations using Lime can be computationally prohibitive. Now, how do we address these challenges? So, that is basically one of our recent works. So, this is an archive preprint that we have recently put up. Basically, our solution to this is thinking of Bayesian versions of these methods, right? But you might wonder or ask, like, how will a Bayesian version address all the problems that we have just mentioned? I'll go through it little by little so that we can get a sense of how. Okay, so let's start here again with the feature importances output by LIME. Okay, so both of these are outputs of LIME. And what you see here is that, this is the explanation computed with 100 perturbations. For example, here you see misdemeanor charges having a feature importance of 0.23. And this is the explanation computed with 2000 perturbations. Here, misdemeanor charge has come all the way here with feature importance of like 0.10, right? So these are ordered in, the descending order of the magnitude of feature importance, right? So what you see between these two is just changing the number of perturbations is giving drastically different explanations, which can be very confusing to the user. Right now, what will be the output of our methods? Let me just show you that. Our goal is that instead of thinking about these feature importances as point-wise estimates, let's think of these as distributions, right? So basically, our output looks something like this, where if the explanation is computed with 100 perturbations, we will have a much wider credible interval here, as you can see, right? And when the explanation is computed with larger number of perturbations, obviously we have much tighter credible intervals. But what you see is there is no conflict between what we were saying with 100 perturbations and what we are saying with 2000 perturbations. It still lies within the credible interval that we have, right? So for example, maybe if you look at priors count, which is this one, here the credible interval is wider, here it becomes narrower, but still this is within this broad interval, right? So that way, at least like a user has a good understanding of, oh, now I'm getting like a more closer to the ground truth explanation or a feature importance as I'm increasing perturbations, but there is no inconsistency or like, something new that I'm seeing, or like my explanation is changing completely, right? That's not the case. Okay, so how do we do it? So this is our generative model. The way we address this problem is to construct a Bayesian locally weighted regression that can accommodate LIME and SHAP weighting functions, right? So what you have here is that, let's say we have a perturbation Z, which is similar to the LIME perturbation, right? So the prediction of that particular perturbation Z is basically Y, and Y is modeled as this kind of a function. Phi transpose Z plus epsilon, phi being this vector of feature importances that we need to estimate, and Z being the perturbation itself, right? And this epsilon is basically allowing us to have like a margin of error for between, what phi transpose Z is capturing and what a prediction of a particular perturbation could be. Okay, so epsilon is modeled this way, which is like a Gaussian with zero mean and this variance, right? The important thing to note here is this function pi x of z, which is basically the similar weighting function that we saw in the case of line, which encourages points that are closer to the instance x that we care about to have higher weights than points that are farther away from that instance, right? So in some sense, again, this is reflecting the notion that your error can be bigger if your point is much farther away, because it may not even be in the local neighborhood. So we don't need to capture that using our local linear model, right? So, and then we have these functions as priors on the feature importance as well as this particular numerator of this error function. Okay, so that's how we model this. And while this might look kind of intuitive on the surface, we made some specific choices in how we chose the distributions and also how we modeled this specifically by including weighting functions. And I'll talk a little bit about what those good aspects of this kind of modeling scheme are. So here is just for the sake of completeness, like some inference output. So basically, based on conjugacy, our posteriors look something like this on feature importance as well as the sigma square, which is the variance of epsilon. And then we can compute all these parameters in closed form. Okay, so here is what the closed form expressions would look like. And if you notice, these are the same equations that are used to compute closed form solutions for like LIME and SHAP, right? So what this is showing is that the mean, the feature importance means that our method compute will still coincide with the feature importance is output by methods like LIME and SHAP. That's because that's by design. We are choosing these parameters to get to the mean feature importances of methods that people love and use so much. But at the same time, we're also creating a whole uncertainty interval around it so that they can know how confident we are about the explanations, right? Okay, so there are two kinds of uncertainty captured by our methods. One is feature importance uncertainty, where we are capturing what is the ambiguity or uncertainty associated with the feature importance's phi, right? And how do we obtain this? We can compute the posterior mean using the closed form solution. So there is this equation from which you can compute the posterior mean, and you can also obtain credible interval around it by repeatedly sampling from the posterior distribution phi, right? So you have this mean here, plug this mean in here, and then repeatedly sample this distribution in order to get this kind of a interval around the mean feature importance. Similarly, we also have the uncertainty associated with the error term, and this can be very useful because it captures how well our explanation models the local decision surface of the underlying black box, right? So, in some sense, the higher this kind of uncertainty around the error, or the higher, like for example, we can compute the probability of epsilon equal to 0, and that will tell us if our local linear model or explanation is a perfect fit of the underlying complex black box model. Okay, so these are some nice pieces that we can do using this method. So there are more interesting and I think nice features here. So the approach that we have, for example, can answer questions like this, right? So let's say a user says, I need an explanation where true feature importance lies within plus or minus zero point 0.5 of the estimated values with 95% confidence, right? So the user is specifying the range, the width of the interval, and also the confidence with which the true feature importance should lie within that width, right? If the user inputs these, we actually have some theoretical results which can help us compute how many perturbations do we need in order to hit those user specifications, right? So we can now compute a precise estimate of how many perturbations are needed if we want to achieve this level of confidence. 95% confidence with plus or minus zero point 0.5 of the estimated values. Okay, there is one more thing that this work basically gives, which is also important, which is addressing the scalability pieces, right? So, and we call this as focus sampling. I'm just going to talk about an intuition here. So, instead of sampling perturbations randomly and querying the black box for their labels, what we do is we choose points the learning algorithm is most uncertain about, and only query their labels from the black box, right? So instead of randomly getting perturbations, we only and asking for their labels, we only choose those points to query the black box for which we don't really know the labels for, or the LIME learning algorithm or baseline learning algorithm is most uncertain about, right? And this actually helps quite a bit also in improving the scalability. Okay, so this approach allows us to construct explanations with user defined levels of confidence in an efficient manner. Okay, so that is, I think, a very unique and nice way to think about explanations. So you're getting reliable explanations with some sorts of guarantees on how good these explanations are. Okay, let's talk a little bit about empirical evaluation. Uh, I just wanted to show you some results here. The first thing is that we compute the fraction of true feature importances that fall within the 95% credible interval, right? So true feature importances, the way we compute them is by running LIME and SHAP for a very large number of perturbations. Again, I just want to say that we only did this for this evaluation. In practice, it would be extremely tricky to run LIME and SHAP for this number of perturbations, right? So we get the true feature importance, and then we see what our estimates look like when we compare it to them. Okay.
Hello, sorry, I think we've just lost Nima for a second, so we're just gonna give her a minute to return to the call. And Wojciech, maybe in the interim, would you be able to explain a little bit about what the objective of the Trustworthy AI series is? And we can contextualize.
Yes. I think, I mean, this talk today very much fits into the whole focus of the series, because we are now also like want to learn about the trustworthiness of explanations. So if we can trust and can develop methods to make explanations more trustworthy. So Hima is back. I think we can continue.
Yeah, sorry about that. Of all days, for some reason today it's giving me some troubles. So yeah, I will just continue again from the evaluation piece. Okay, all right. Yeah, so we were talking about this first result where we were computing these true feature importances by running LIME and SHAP for a very large number of perturbations, and then seeing how well our estimates calibrate with those of these true feature importances, right? While we compute true feature importances this way, it is extremely hard to do so in practice. We just did it for a small scale experiment. I just want to put it out there, okay? So on standard data sets, what you see is these numbers. So just to give you a sense of what is a good number here, the closer to 95 these values are, the better, right? So in some sense, what we are saying is if we generate estimates using our baseline based SHAP methods, what fraction of the time are the true feature importances falling within this range, right? And the closer to 95% that number is, the more calibrated our estimates are. As you can see with baseline, we have a pretty close calibration. So a lot of these numbers are much closer to 95, whereas like with base SHAP, we have a slightly lesser calibration, but still it's not too bad. It is like pretty close between, 90 and 87 and so on, right? There is one more experiment that we did in order to evaluate the correctness of the number of perturbations. And the way we were trying to evaluate this was that, let's say if we specify a particular the interval width and then confidence interval, like fix the confidence interval as 95%, the confidence level as 95%, and then let's say we try to have like input like the desired width. So we start all the way from 5e minus 3 and keep increasing that desirable width. And then we see what is the observed width that we achieve using our explanations, right? So if our number of perturbations is well calibrated and correct, we should see that the observed width should roughly match the desired width. And that's precisely what you see here. A lot of times these observed width just matches the desired width here. Okay, so that is pretty much how we think about it. Okay, then we also looked at the stability, and here we computed the percentage increase in stability compared to baseline in this top plot. And what we see is we actually see big improvements in stability here, closer to like this mean improvement here being like somewhere around 60%. But basically, we see much bigger improvements in stability compared to previous methods like LIME and then SHAP, right? So there is one small dip here. We are still investigating like why there is that dip for this particular data set. But other than this one data set, we see consistent improvement throughout in other cases, right? And we also did one user study here where we were basically trying to assess if LIME explanations are better or worse than the explanations generated by our approach, which is baseline. And the way we think about this experiment is that let's take the most important features output by LIME, mask them from an image, right? So we are doing this image recognition task, mask them in an image, and then do the same thing for our approach baseline. The most informative features, when they get masked, that's when people have the most trouble recognizing what's in the image, right? So that way we can see that if I remove the most important features from the image that were given by LIME, if I do the same for this other image given by our approach baseline, and we show to the user and say, now go recognize this digit after we remove those important pieces, if the users make more mistakes with, let's say, our masked images versus like LIME masked images, then maybe we have more important or more informative features, because removing those is making it harder for users to assess what is in the image, right? And the idea here, as I just mentioned, is the better the explanation, the more difficult it should be for the users to get it right when corresponding top features are masked. Okay. And the user error rate, as was expected, was like lower for LIME, which kind of concurs with the hypothesis that maybe the features output by LIME are not as informative, and it was higher for the error was higher for baseline, indicating that the features that we output were probably more informative, and because of removing them, users were very thrown off, right? So yeah, our explanations generated by baseline are more informative than LIME explanations is one possible conclusion from this. Okay. So I will just go through very quickly for a couple of minutes one other approach I just wanted to cover, which is about explanations that are robust to distribution shifts. So I'll be touching a little bit upon global explanations to explain this approach. And just to give you a spiel about what a global explanation is, the goal here is to explain the complete behavior of a given black box model, and basically to provide a bird's eye view of the model behavior, right? So these explanations help us detect the big picture model biases persistent across larger subgroups of the population, because it is sort of impractical and highly challenging to manually inspect local explanations of several instances to ascertain big picture biases. And global explanations can be thought of as being complementary to local explanations. These ones provide a bird's eye view, local explanations sort of provide a more zoomed in view, right? That's one way to think about it. While again, there are several strategies for global explanations, one strategy that has been used commonly by at least a few approaches is that of model distillation. And what is happening here? The approach is actually very simple. So let's say we have some input data and we have this black box that we want to explain. We just throw the data into the black box and then we get the model predictions. And we take everything as an input to this explainer algorithm, and we output just a simpler interpretable model that just mimics this algorithm, right? That just mimics this black box. So think of it as like, you have a complex model like a deep neural network, and then you're essentially fitting a decision tree to make the same predictions as that of the deep neural network, right? So you are just training a decision tree to mimic the predictions of this deep neural network. So that is roughly model distillation, right? And one of the challenges with this kind of approach is that they can be highly data independent, right? And what do I mean by that is that, let's say there is some distribution P of x1 comma x2 where x1 and x2 are perfectly correlated, and then there is a black box which is basically saying that the prediction should be 1 if x1 is greater than or equal to 0, otherwise the prediction should be 0, right? Now, since these two are actually correlated, your explanation can be something like this, which is just based on x2, and it has perfect fidelity. But as you can see, this is a very different thing than what the model is trying to do, right? But it still has like perfect prediction match. Okay, so that could be a problem. And most of these model distillation approaches optimize for prediction match, right? And why is this a problem? If you give like these misleading explanations, they can cause confusions to experts, and that is a problematic piece, right? And what do we do? I'll just show you the objective here. We try to use adversarial training in order to mitigate this problem, right? So here is like a standard supervised learning loss where we are trying to ensure that the explanations output matches the black box model's output. And then that's what a standard explanation method loss also looks like. But what we are adding here is this kind of a max where we think of a worst case distribution, worst case over the distribution shifts, right? So we are not just doing an argument of this standard loss, we are introducing this term here, which is basically saying minimize the worst case loss over possible shifts of the instances in the data, right? So that way you're making these explanations more kind of data independent, so that there is like a more of a capture of the behavior of the model as opposed to just like being highly data dependent, right? So yeah, that's this approach. And when we evaluated this on a bunch of real world data sets with distribution shifts, what we found is that with these approaches, like the last two approaches, the drop in this kind of fidelity, which is basically the prediction match, the drop is like much less between the source and target data sets for these methods, like our methods, compared to the drop that is occurring in case of like other generic global explanation methods, showing that these could be potentially highly data dependent, whereas we are trying to break that data dependence, at least for like global explanations. And this approach can also be applied to, and we have seen improvements with certain kinds of local explanations as well, right? But the main point being, this approach is like helping explanations to be more robust to distribution shifts without sacrificing fidelity on the original data. Okay, so with that, I just wanted to point out some conclusions and then close. There is like a very critical need to rigorously evaluate explanation methods, thinking about, are they accurate, how to determine that, can they mislead users, again, how to determine that. These questions, while there are some answers, we don't have like exactly the most foolproof answers, and more work is definitely welcome and required. Improving the reliability of explanation methods is key. What I try to present in today's talk is just a first step towards this. There is a lot more stuff here to be done. And another thing that I think we should also push for is to think about a more interactive and dialogue-based approach to explaining models, as opposed to thinking about explanations as here is just a one-shot approach, right? So that also becomes critical. With this, I would like to thank all our sponsors. I just wanted to give a special mention to a couple of our industry collaborators with whom we are studying how people are using explanations in practice. For example, with Fiddler, we are studying how developers and data scientists are using explanations. With Altabi, which is another amazing startup in the Middle East, and they're working on how AI can help doctors in making better decisions. So we are also partnering with them to understand the needs of the healthcare providers. So I also just wanted to flash this slide and point you all to this link on Trustworthy ML for more resources on explainability. Thank you so much, and happy to take any questions.
Yeah, thanks a lot for this very insightful talk. So let us start with the Q&A. We have a question in the Q&A chat. So the question is, does this approach, I think this is referring to the to the global explanation approach, only apply to supervised learning approaches? So do you need labeled data for that, or can you extend it also to unsupervised learning, for instance?
That's a great question. So, all the approaches that I talked about today, and more generally in the explainability literature, they mostly look at the labels assigned by the model, and there is very little bearing on the exact ground truth labels, right? So, let's say you have a data set, you don't have actual ground truth labels for it, but you do have a model that can make predictions on that. That's all that is needed, because you're ultimately trying to explain the model, and not the properties of the data and so on, right? So the same case applies with both the global explanations I talked about, as well as the previous local explanations I talked about in the first section.
So I also have one. So I'm also very interested in the aspects of evaluating explanations. And I wanted to hear your opinion about evaluating things with synthetic data set, or where you kind of know the ground truth. So we recently published a paper where we kind of use a clever data set to design scenes where we can, and then we can ask a question and we exactly know which objects in the scene are relevant to answer this question. So do you think these approaches have some limitations, or what is your opinion on these kind of evaluation schemes?
That's a great question, because that also touches some of the things that we have been scrambling with in our daily, weekly meetings these days. So I would definitely say there is a lot of merit to thinking of synthetic data or models, right? Like, for example, let's say if I have an underlying linear model, and let's say if I run LIME, so I can literally just compare the two feature importance vectors and see how good LIME is doing if this was my underlying model, right? So that is giving me a very clear picture of, is this capturing exactly what this model is, right? So I think those evaluations are definitely important, should be there. And same thing as you're mentioning, maybe the data has some properties and you're trying to see if your explanation can reflect that. In that, I would just add one more note, which is that I think if there is data which has some properties, if there is a model that is trained on this data, and then we have the explanation, so the explanation is still going to explain what the model does and not what the data has. So I think checking that would be important, to see if the model is actually reflecting the data properties that we want it to reflect, and then we can make sure that the explanation is reflecting the properties that the model is capturing, right? But if that pipeline is good, then obviously it makes a lot of sense to have these synthetic data sets. One caveat that as we were brainstorming, that we were thinking about more was, while these are great ways, and I think they should become part of evaluation, there is no doubt about it. The other side, though, also is important, because if we restrict ourselves to this, I think on some level we will always be constrained by everything just being tied to these synthetic pieces. And what if these are not representative of all the messy data sets out there, right? So I would think of this as both are important, but I can definitely see a lot of value, especially in a first cut evaluation of how good is this explanation. Let's have a synthetic model that we know, let's have a synthetic data that we know, and a model that captures its properties, and that will give us a very, very clear picture without any doubt and confusion.
So we have another question from the audience. Could you elaborate more about the idea of an interactive dialogical model interpretation technique? I think this is also very, very, I also think this is very important in the future, to have explanations which are not only one-shot explanations, but do you have any work on that? Do you have any ideas how this could look like?
Yes, that's a good point. I can just post like one of our papers earlier. Again, I just want to start with the caveat that this is basically like one of the first steps, and we have like a big grant on this and so on, and we are working more. But like if you look at this, in some sense, this is, I would not say this is super dialogue based, but it is at least some level of interactive, in the sense that a user can say, here are the attributes that I care about, or the subgroups that I want to see what my model is doing there, right? So for example, gender based, sort of splitting of the data, or like income, maybe age, like if the person cares about how for different values of income and age the model is behaving differently, right? So users can put in those features, and then the model will automatically create subgroups based on those features, which give us a high level overview of like how differently or similarly a model might be behaving in those subgroups, right? Of course, it's again like a very initial approach and so on. So I think there's scope to do a lot more. We are actually also thinking about like what could a sequence of explanations look like when we are trying to explain a model
Mhm.
to somebody, right? And
Mhm.
thinking about if there is maybe a doctor who is like training, like a resident, right, like a new resident and just started training, what would the explanations look like for them versus like what would the sequence of explanations look like for a more senior doctor who has had
Yeah.
more experience with like parsing these scans and data and so on, right? So we are thinking about what is an optimal sequence of explanations to show based on user preferences and so on.
Very, very interesting. I also saw some talk from Berkeley where they applied this kind of ideas for VQA, where
Yeah.
they had like this multi-step explanations. I think this is something which we should, as a community, look a bit more in the future. Another question about the focus sampling and scalability of LIME or of these kind of approaches. So you said that you can improve uh, or reduce the number of points you need to sample by having like more focus sampling. Can you elaborate a bit more on that?
So elaborate a bit more on just the details of what focus sampling is doing.
Yeah, I could imagine that if you do it wrong, you can introduce some bias,
Right.
maybe. So what are the risk about that, and like how much can you save? Can you make these approaches really like applicable for large models, or is it still like
Yeah.
the computational very heavy?
Right. Yeah. No, that's a great point. And I just want to start by saying, like, I think this is particularly useful when your complex black box is extremely complex, that even querying a label from it is going to take some time, right? This is where we were doing experiments with like InceptionNet, AlexNet type models, where even the query time is non-trivial if you make like a million queries, for example, right? So that's where it is most useful for. But I think the bias piece is very interesting because we also have some results in the paper about that. So where we actually again thought about this, that when you do like a random sampling of perturbations and query the model, obviously you're not having like any other kinds of biases. But what we are doing is saying that, oh, LIME is most confused about this, the label of this particular instance. So let me only pick the instances that LIME is most confused about and then ask the model for its labels, as opposed to asking any random sample. It is helping a ton with the time taken, like the clock time. I think we see an improvement depending on the data we are looking at, anywhere between like 3 to 8 times. So there is a huge improvement in terms of making things more efficient. We also did some checks in order to see if this is leading to any bias, like are the explanations that we are getting any different when we do this than what we would get with like a random sampling. And it turned out that like there is some bias, especially in some data sets we can at least see some bias, but in general the bias is not as pronounced, because that's something that we worried about a lot in the beginning, but it turned out that the bias is not as pronounced generally across like the whole gamut of typical data sets that we look at, like ImageNet, MNIST, Compass, and so on. But the scalability improvements are way more pronounced, and it is particularly helpful with like very big models, very complex models.
So I have a question regarding like trustworthiness of the model. So I mean, one focus of this workshop series is to think about like or like summarize the state of the art in, yeah, can we make sure that our model is trustworthy? How can we certify a model? How can we test it? How can we audit a model? So do you think explanations must be a key component in such an auditing process? Or like what can explanations kind of contribute to either make your model more trustworthy, or to do the testing of your model, or the evaluation of your model yeah, more secure, that in the end you will have maybe a model for a medical application, and through this process we want to ensure that this is really safe and trustworthy. So what can explanations contribute in this process?
Yeah, no, I think that is another great question. So, if we want to assess or ascertain if a model is sort of quote unquote trustworthy enough to be deployed in a setting, I would start by saying that we should do multiple checks, not just think of let's do an explanation and then we are good and like throw it out, because it's interesting that I have seen that happen in practice, especially with like, new healthcare companies and so on. They were looking at like LIME results and saying that, oh yeah, look, my model is doing all the right things, like I'm just going to like use it in deployment, right? And that's what actually motivated some of our earlier work on how like these explanations could be very misleading. I would say like explainability should definitely figure in that list of checks that one should do in order to ensure a model's trustworthiness. But it should not be the only check. Like, I think people should check for other key things, like do some statistical parity checks for fairness, equality of opportunity tests to ensure fairness, and adversarial robustness tests as well separately. But in that whole suite of tests, I think explainability should also play a huge role. But I also want to caveat that by saying that it is, I mean, explainability is still like, in my understanding and belief, still in somewhat of nascent stages. Like, we don't have approaches where we can say, oh yeah, just run this and you're good to go, right? Like, it's not still like completely solidified. It's still in like, yeah, we are testing, we are improving in that process, in that stage of, sort of research and development, I would say at this point. So my advice would be, if somebody wants to ask today, okay, what should I do to make sure this model is trustworthy? Of course, do all the checks and also explainability checks, but maybe try a bunch of different approaches to see what are the different kinds of explanations they are producing, because there is always some iffiness around, especially some of the most popular approaches, like we were talking, and several papers, including some of our work, have showed that there is some iffiness around these explanations, right? So the best way to sort of deal with that, all this like messiness, is at least run multiple explanation algorithms to see what they are generating. And you should develop an aggregate idea about what your model might be doing, as opposed to just saying, oh, I've run LIME and like we are great.
Okay, so maybe one last question about the uncertainty. I think you said that you could pick the points where the model is most uncertain about in the sampling. And the question is, isn't the process of finding out uncertainty in itself very inefficient or costly or complex?
Yeah, that's a great question. And I think if I mentioned somewhere in between, hopefully that was not like when I was cutting out or something was going on. But basically, one of the reasons we formulated that generative model in the way that we did was that it is allowing us to get closed form expressions for the different model parameters, right? So normally, yes, of course, if you're doing a Gibbs sampling or like variational inference, these processes are expensive, and there are like other challenges associated with them and so on. But like one of the reasons we stuck to a very specific formulation and didn't deviate, because you could do this Bayesian modeling in different ways, is that this is allowing us to get like closed form, like you can just compute one expression and you will get the value of a parameter, right? So it was helping us kind of sidestep a lot of these typical challenges associated with like computing uncertainty or Bayesian models.
Great. So Hima, thanks a lot for this insightful discussion and the great talk. And yeah, with that, thanks a lot, and take care.
Sure. Thank you so much. Thanks for having me. Thanks everyone for your time.
Bye-bye.
Thank you, Wojciech, and big thanks also to Hima for today's discussion. So we hope that you enjoyed the discussion today, and we're launching a quick poll that you can see right now on your screen, and you can say how much you liked it. In the meantime, let me say that we have several interesting sessions come up, and we're posting the links and the information about that in the chat right now. So please have a look once you've voted. And with that, I think we've come to the end of today's session. So thank you very much, and I'll see you tomorrow.